Okay, hello, everyone. We're moving on to the theory for Chapter 5, and Chapter 5 is kinetics. So, for the last four chapters, we've been using kinematics, and that's motion stuff. Now, this is kinetics, where we're talking about the changes in motion and the forces that cause these changes in motion. And the forces that cause these changes in motion. Right? So, beforehand, we were just doing kinematics, which was motion without a cause. So it was just motion. Now, all of our motion has cause. So, that doesn't that changes what formulas we'll be using mainly, right? And we'll start with the basics, which is F equals ma. This is Newton's second law, which is the force on a particle and its acceleration are proportional, right? You should also already know Newton's second law from like high school. If you didn't learn it in high school, I'd be a little concerned about the teaching quality of your high school. Um, but yeah, this is Newton's second law. So F equals ma. Newton's first law was F equals zero, but that's statics. We don't care about statics because this is dynamics. Yeah. So you have F equals ma, and then force can be split into. Force is a vector, right? So you can have force vectors. There we go, force vector F, right? So that means it can be split into X and Y components, which is necessary when doing calculations if it's not already in just one direction. Yeah. So there's a few different types of force, right? One of the most important ones we need to know is the force of gravity, also known as weight. So W for weight, right? The formal theory for this is m1, m2, g, capital G, which is the gravitational constant, over radius squared, right? But if you were to plug in m2 of Earth and then the radius of Earth squared, that whole term, the m2 capital G over r squared, that just becomes lowercase g, which is gravitational acceleration. So weight is equal to mg. And as you can see, these equations are basically identical. It's just that our g is constant in this case on Earth because, yeah, gravity is constant. So basically, weight is a constant term, is what we're being told here, compared to force, which can be variable because of variable accelerations, right? And that's like the most fundamental force. Some forces don't actually have equations. You have to build them up from equations, like from the force, the sum of all forces. You have to build up from there. And then some do have equations, like, yeah. Anyways, let's move on to equations of motion, or the equation of motion, sorry, is, so we have sum, sum, okay. Oh, I don't have my hotkeys on. Oops, sorry. I always forget to turn that on before I record. Oops. No? Okay, I don't even have that. Sorry, that was kind of a waste of time. Anyways, the sum of F is equal to F sub R, which means resultant force. Okay, and then this is equal to MAR, where AR is the resultant acceleration. That's about it. It's basically saying that all your forces will be adding up together. So there are two things that we're going to be doing now in this unit. which are free body diagrams. So let's say you have this ball, right? And it's on the ground. And you're pushing it this way. Pushing this way. You're putting a force on it like this. Draw the free body diagram and draw, this is going to be new, a kinetic diagram, which is basically the diagram of its acceleration. So I'll start with the free body diagram down here. So we're going to have ball as our particle. And then we're going to have one F this way. FA for force applied. Normal force going up. And normal force is the opposite reaction to gravity. And it's part of friction as well. And then we have weight or gravity down here. Usually when I draw free body diagrams, I don't actually write weight. I write mg. Like equal. I don't actually write W equals mg. I just write mg down here. You don't have to. It doesn't really matter. That's just how I do it. And now the kinetic diagram. So this is the free body diagram. So FB, free body. Now the kinetic diagram. This is really easy. As you can see here, these two forces cancel each other out. The normal and the weight. They cancel each other out. So we have no vertical acceleration. And we have one force going this way. Realistically, there'd be a bit of friction pulling back. But we're assuming frictionless surface because that's more fun. And there you go. That's your kinetic diagram. Kinetic diagrams are really easy. It's like a circle. And that's it. It's just rewriting force as MA. Right? This is a kinetic diagram. So, kinetic diagram, free body diagram, original problem, right? Nice and easy. And some things we need to know from this equation is that if FR is 0, that means we have no acceleration. So what does that mean? That can mean constant velocity. It can also mean no velocity at all. It's just not moving, right? There's always going to be a position, so that's not a thing. It can be 0 position, like it could be on the origin, but it'll still have a position. But basically, it's either at rest or it's at constant velocity if the resultant force is 0. That's what that means. Anyways, so now we're going to get into what I was talking about earlier, splitting it up into its coordinates. So F is a vector. So that means it has ijk components. And so that means it has an f of x I plus fy j plus fzk. That's supposed to be capital F. fzk, like that, right? And same thing for acceleration, right? Acceleration also can be split into its components like this. So what does that mean? It means that since this is sum of f, right? Do I really not have this hotkey? No, I don't. Okay. Since it's sum of f, that's saying that the sum of fx is equal to max. And then the same thing, but for all the other terms. So for the y and the z. So this is z, and this is y. Right? That's basically all that means. Nice and easy. And actually, that's kind of all there is to kinetics. These chapters are really, really short. I'm going to be honest. Most of dynamics, at least in when I was getting the lectures and stuff, was just really short introductions to theory stuff. So like something of this length, and then practice problems, because that's the best way to teach and learn dynamics, is just practice, right? So that's why all these videos are really short. I guess I can do like okay, well, there isn't really anything else to do. Friction is going to come up later. So for now, unless it explicitly states in a problem, We're just going to be saying that there is, or wait, no, we will have friction. I should go over the force of friction. You're supposed to know these like forces already, right? But I will just reiterate because they're just like formulas and stuff, right? So we have the force of friction, so Ff, which is equal to mu mu n, right? Yeah. So this is kinetic friction, by the way. There's two types, static friction and kinetic friction. So this would be mu k n. Let me just put a x here for multiplication. And then there's the same thing but with an s for static friction. I'll go into more detail about those when it when it's actually needed. So that would be like way later. It comes up more in like chapter 7, I think, if I'm remembering right, is when friction becomes a big thing. In like we need to be like actively aware of it instead of just using these formulas, right? But static friction is like the amount of friction it takes to stop your thing from moving. So like if we have this diagram, right? If we had a force of friction that's equal, and friction is usually lowercase f actually, not there's no capital F. So it'd be like this. Fk Fs, like that. That's how you would write it. If you have this, you'd be given, like in the problem, you'd be given a static, this is a constant, by the way, coefficient of friction, I think. Yeah, that's what it's called, coefficient of friction. That's constant. So you'd be given one for static friction, and it'd be like, this is the static coefficient of friction. So you calculate the amount of force, like the amount of static friction there is, and let's say it's 100. So to surpass that, you'd need your Fa to be more than 100, and then the ball would start moving. So the question would be like, here's a variable force Fa. Here's your static friction. How long will it take until until the ball starts moving, right? So then you calculate Fs, static friction, and then you set it to where you're solving a inequality thing, or yeah, you do like Fa greater than Fs, and that's it. And then once it starts moving, you switch over to kinetic friction. When something's in movement, it experiences kinetic friction. But I'll explain that more in depth later, probably. One more force is F sub S. So spring force is what was spring force? K delta S. That's spring force. K is the spring constant, and delta S is the change in position. Right? Those are just some examples of some simple forces. Yeah. So solving the questions is really easy. You're just going to check your coordinate system. Like choose what you're setting as a positive. You're going to you need to make a free body diagram and kinetic diagram. Get into the habit of making that, not just if the question's asking. It's always helpful to organize everything onto one diagram, because you could have like you could have like this happening on the ball. These are all forces, right? But if you organize it onto one diagram that's nice and clean with all your forces laid out like this, we could change this Fa to Fr. Like it's the sum of all forces, right? We can change it to Fr. Like there's 3 forces on it. Instead of displaying 3 forces, you calculate and you display it as Fr. So now you're more organized, right? So always get your free body diagrams. Let me redraw the kinetic diagram here quickly. Like that. M-A-R. There. And then after that, you do force analysis, which is like setting your things equal. Some of the forces in X, some of the forces in Y, some of the forces in Z. This is force analysis, this part here. The components is the analysis. You can also use kinematics, depending on the problem. If you have constant acceleration, bring in kinematics. Even if you don't, we have these, right? These properties here. I mean, these relationships. So you can use those, and just stick to x, y, and z coordinates for now. We'll be going over like normal and tangential kinetics in chapter 6, which is, honestly, I don't really know if I need to make a theory video about that. There isn't really any theory. Um, huh. Okay, I'm gonna put chapter 6 into this video as well, because there's no theory. There's like nothing at all about there's no content. So chapter 6 is normal tangential kinetics. Right? So this is all the same. We're just going to be saying now that instead of breaking f into these components, we're going to break f into ft, fti, f, n, j, and fb. B is binormal, so that's like your three-dimensional direction. It doesn't really mean anything, but yeah, that's all. This is chapter 6. This is everything else is the same. It's just some of the forces in T, some of the forces in N, some of the forces in B. Nothing else changes. I'll rewrite these just for the sake of it. B, N, T, and T. Also, usually the sum of the forces in the binormal direction is 0. This is like usually. So I'm going to say equals 0 usually. Like that. And MAN is V squared over rho. So keep that in mind. MAT is dV dt. So this is also MV prime. So there you go. This is supposed to be an equal sign. That's it. That's this chapter. That's 2 chapters done. So, yeah. Thank you for watching. Oh, now I need to think about the problem video. I have enough problems for each chapter to make them separate videos. So I'll make them separate videos. That's fine. Okay. Thank you for watching. Bye.